The National Electrical Code, or NIC, establishes a 40% maximum fill limit for conduits when dealing with cables and a 53% limit for individual conductors. However, it's important to note that these specifications primarily address high-voltage applications, generally those exceeding 600 volts. When considering low-voltage wiring systems, those operating below 600 volts, the NEC provides less specific guidance regarding conduit fill. In these situations, it becomes crucial to refer to the guidelines and recommendations provided by the manufacturers of the conduit and cables themselves. For a specific example, when using 18/4 plenum rated wire, manufacturer guidelines suggest that a 1-inch conduit can typically accommodate 6 to 8 wires without the need for dirting. However, if you intend to install between 9 and 12 wires, it will be necessary to implement dirting practices. Dirting involves reducing the allowable current carrying capacity of the conductors to account for the increased heat generated by the high density of wires within the conduit. Several key factors influence the number of wires that can safely and effectively be installed within a conduit. These include the specific type of conduit being used, as well as the characteristics of the wire itself. Dirting becomes essential when the conduit fill exceeds 40%, because a higher concentration of wires increases heat and you need to account for the reduced ability of the system to dissipate heat. It is always advisable to consult the manufacturer's instructions. In addition to the fill limits, several other considerations come into play when determining the appropriate conduit fill for low-voltage wires. Firstly, the material of the conduit itself is a significant factor. For instance, electrical metallic tubing, or IMP, offers greater flexibility compared to polyvinyl chloride, or PVC, conduit. This flexibility can facilitate the process of pulling wires through the conduit, potentially allowing for a slightly higher fill capacity. Secondly, the insulation of the wires impacts the amount of space they occupy within the conduit. Thicker insulation naturally requires more space, which in turn affects the overall fill capacity. Thirdly, the number of bends in the conduit run must be taken into account. Each bend reduces the available space for wires and increases the difficulty of pulling the wires through the conduit. Fourthly, it is crucial to manage the pulling tension applied to the wires during installation. Excessive pulling tension can potentially damage the wires or the conduit, leading to future problems and safety hazards. As a general best practice, it is recommended to adhere to the manufacturer's recommended fill limits when installing low-voltage wires in conduit. Following these guidelines helps ensure adequate heat dissipation, minimizes the risk of damage to the wires or conduit, and maintains compliance with the NEC requirements for electrical safety. The goal is to create a safe and reliable electrical system that functions optimally over its intended lifespan. Understanding and applying these concepts of conduit fill ensures electrical installations meet industry standards. The NEC serves as a comprehensive guide for electrical installations, but it is not always highly specific for low-voltage applications. The NEC provides a foundation. It needs to be complemented by manufacturer specifications and industry best practices. This approach ensures electrical systems are safe, efficient, and compliant with all applicable regulations. Furthermore, proper conduit fill is essential for maintaining the longevity and reliability of electrical systems. Overfilling a conduit can lead to overheating, insulation breakdown, and potentially electrical failures or fires. By adhering to recommended fill limits, electrical professionals can mitigate these risks and ensure the long-term performance of electrical installations. In addition to the physical considerations of conduit fill, there are also practical aspects to consider. Overfilled conduits can be difficult to work with, making it challenging to pull wires through during initial installation or when making future modifications or repairs. This can lead to increased labor costs and potential delays in project completion. Therefore, proper planning and adherence to fill limits not only enhance safety and performance but also improve the overall efficiency of electrical work. The selection of appropriate conduit size is another critical aspect of electrical installations. Choosing a conduit that is too small can result in overfilling, while selecting a conduit that is too large can be unnecessarily costly. Electrical professionals must carefully assess the number and size of wires or cables required for a particular application and select a conduit size that provides adequate space without being excessively large. This process often involves consulting conduit fill charts and tables provided by manufacturers or found in the NEC. These resources provide guidance on the maximum number of conductors of a given size that can be installed in various sizes of conduit. In addition to conduit fill, it is also important to consider the type of conductors being used. Different types of conductors have different insulation thicknesses and heat dissipation characteristics, which can affect the overall fill capacity of a conduit. For example, conductors with thicker insulation may require a larger conduit size to accommodate the same number of wires. Similarly, conductors with better heat dissipation properties may allow for a slightly higher fill capacity. Electrical professionals should carefully select conductors that are appropriate for the intended application and consider their impact on conduit fill. Another factor to consider is the presence of splices or terminations within the conduit. Splices and terminations take up additional space and can obstruct the flow of air, potentially leading to overheating. Therefore, it is generally recommended to minimize the number of splices and terminations within a conduit run and to ensure that any splices or terminations are properly insulated and secured. When planning electrical installations, it is also important to consider future needs. Electrical systems often need to be expanded or modified over time to accommodate changing requirements. Therefore, it is prudent to select a conduit size that provides some extra capacity to accommodate future wiring additions. This can save time and money in the long run by avoiding the need to replace the conduit if additional wiring is required. In addition to the NEC and manufacturer recommendations, there are also industry best practices that can help ensure safe and efficient electrical installations. These best practices often involve using specialized tools and techniques to facilitate wire pulling, such as wire lubricants and pulling grips. These tools can reduce friction and pulling tension, making it easier to install wires and conduit without damaging them. Another best practice is to properly label and identify all wires and cables within the conduit. This makes it easier to trace wires and troubleshoot problems in the future. Wire labels should be durable and resistant to fading or abrasion to ensure that they remain legible over time. Regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. Conduit runs should be inspected periodically for signs of damage or deterioration, such as cracks, corrosion, or loose fittings. Any damaged component should be repaired or replaced promptly. In addition, wire connections should be checked for tightness and corrosion, and any loose or corroded connection should be tightened or replaced. Electrical safety is paramount in all aspects of electrical work. Electrical professionals should always follow proper safety procedures and use appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools. They should also be aware of the potential hazards associated with electrical work, such as electric shock, arc flash, and explosions, and take steps to mitigate these risks. In conclusion, understanding conduit fill limits for low voltage wiring is essential for ensuring safe, efficient, and compliant electrical installations. While the NEC provides general guidance on conduit fill, it is important to consult manufacturer recommendations and industry best practices for specific applications. By carefully considering factors such as conduit material, wire installation, number of bends, and pulling tension, electrical professionals can select appropriate conduit sizes and install wiring systems that meet all applicable requirements. Furthermore, regular inspections and maintenance are essential for ensuring the continued safety and reliability of electrical systems. By following these guidelines, electrical professionals can help protect people and property from the hazards of electricity. The considerations involved in conduit fill are intricate, requiring a thorough understanding of electrical codes, material properties, and installation techniques. Firstly, the type of conduit material significantly influences its fill capacity and suitability for different environments. Electrical metallic tubing, known as EMT, is a popular choice due to its lightweight nature and ease of installation. It is typically used in dry, indoor locations and offers good protection against physical damage. Rigid metal conduit, RMC, is a heavier, thicker option made of steel or aluminum, offering superior protection against impact and corrosion. It is commonly used in harsh environments or where greater mechanical strength is required. Polyvinyl chloride conduit, PVC, is a non-metallic option that is resistant to corrosion and chemicals. It is lightweight, easy to install, and suitable for underground or wet locations. Flexible metal conduit, FMC, provides flexibility for connections to motors or other equipment that may vibrate or move. It is typically used in short runs and requires fittings for secure connections. Each of these conduit types has different inner diameters and bending radii, which affect the number and size of conductors that can be installed. Secondly, the selection of conductor types plays a crucial role in determining the allowable conduit fill. Conductors are available in various materials, insulation types, and sizes, each with specific electrical and physical properties. Copper conductors are widely used due to their high conductivity and corrosion resistance. Aluminum conductors are lighter and less expensive than copper but have lower conductivity, requiring larger sizes for the same current carrying capacity. Insulation types such as thermoplastic high heat resistant nylon coated (THHN), thermoplastic high heat resistant water resistant (THWN), and cross-linked polyethylene (XLP) determine the conductor's ability to withstand heat, moisture, and abrasion. The NEC specifies the allowable ampacity of conductors based on their size and insulation type, which must be considered when determining the number of conductors in a conduit. Thirdly, derating of conductors is a critical concept in conduit fill calculations. When multiple current-carrying conductors are installed in a conduit, the heat generated by each conductor can raise the overall temperature within the conduit. This increased temperature reduces the ampacity of the conductors, requiring derating to prevent overheating and insulation damage. The NEC provides tables and formulas for calculating derating factors based on the number of conductors, ambient temperature, and conduit fill percentage. Derating must be applied carefully to ensure that the conductors can safely carry the intended load. Fourthly, the number and radius of bends in a conduit run have a significant impact on the ease of wire pulling and the allowable fill. Each bend increases the friction between the conductors and the conduit, making it more difficult to pull wires through. The NEC specifies minimum bending radii for different conduit sizes to prevent damage to the conductors during pulling. Excessive bends, or bends with radii that are too small, can lead to insulation damage, conductor breakage, or even conduit collapse. Fifthly, wire pulling techniques and equipment play a crucial role in ensuring successful conduit installations. Proper wire lubrication reduces friction and pulling tension, making it easier to pull wires through long or complex conduit runs. Wire pulling equipment such as pulling grips, fish tapes, and power pullers can further assist in the process. It is essential to use the correct tools and techniques to avoid damaging the wires or conduit during pulling. Sixthly, the presence of splices, terminations, or other devices within the conduit must be considered when determining the allowable fill. These devices take up space and can obstruct airflow, potentially leading to overheating. The NEC specifies requirements for the size and spacing of junction boxes and other enclosures to ensure adequate space for splices and terminations. It is important to minimize the number of splices and terminations within a conduit run and to ensure that they are properly insulated and secured. Seventhly, future expansion and modification should be considered when designing conduit systems. It is often prudent to install larger conduit sizes than initially required to accommodate future wiring additions or changes. This can save time and money in the long run by avoiding the need to replace the conduit if additional wiring is required. Conduit systems should also be designed to allow for easy access for maintenance and repairs. Eighthly, proper documentation and labeling are essential for maintaining and troubleshooting conduit systems. Conduit runs should be clearly labeled with their size, type, and the circuits they serve. Wiring diagrams and as-built drawings should be maintained to provide a record of the conduit system layout and conductor routing. This documentation can be invaluable for future maintenance, repairs, or modifications. Ninthly, regular inspections and testing are necessary to ensure the continued safety and reliability of conduit systems. Conduit runs should be inspected periodically for signs of damage, corrosion, or loose fittings. Wire connections should be checked for tightness and corrosion. Insulation resistance testing can be performed to detect insulation damage or deterioration. Any problems should be addressed promptly to prevent electrical hazards. Tenthly, adherence to the NEC and other applicable codes and standards is paramount in all aspects of conduit installations. The NEC provides comprehensive requirements for conduit fill, conductor opacity, dirting, and other aspects of electrical installations. Local codes and standards may also impose additional requirements. It is essential to consult and comply with all applicable codes and standards to ensure safe and compliant electrical installations. The principles of conduit fill extend beyond the immediate installation process. They influence the long-term performance, safety, and maintainability of electrical systems. Overfilled conduits can lead to a cascade of problems. The restricted airflow hinders heat dissipation, causing conductors to operate at elevated temperatures. This accelerates the degradation of insulation, leading to a reduction in the conductor's current carrying capacity and an increased risk of short circuits or ground faults. Furthermore, the increased heat can damage the conduit itself, particularly if it is made of PVC or other temperature-sensitive materials. In addition to the electrical hazards, overfilled conduits can create significant challenges for maintenance and repair. The tightly packed conductors make it difficult to access individual wires for testing or replacement. This can lead to increased labor costs and extended downtime, especially in critical applications. The strain on the conductors during pulling and the limited space for maneuvering can also increase the risk of damaging the insulation, creating potential safety hazards. The selection of appropriate conduit sizes and fill percentages is not merely a matter of compliance. It is an investment in the long-term reliability and safety of electrical systems. By adhering to recommended fill limits, electrical professionals can minimize the risk of overheating, insulation damage, and other problems that can compromise the performance and longevity of electrical installations. A well-designed and properly installed conduit system not only protects the conductors from physical damage and environmental factors, but also facilitates future maintenance and modifications. This ensures that the electrical system can continue to meet the evolving needs of the facility without requiring costly and disruptive overhauls. The importance of conduit fill extends beyond the technical aspects of electrical installations. It also has implications for energy efficiency and sustainability. Overfilled conduits can increase the resistance of conductors, leading to higher energy losses and increased operating costs. This is particularly significant in large commercial or industrial facilities where electrical systems are heavily loaded. By optimizing conduit fill and conductor sizes, electrical professionals can minimize energy losses and improve the overall efficiency of electrical systems. Furthermore, the selection of sustainable conduit materials, such as recycled steel or PVC, can further reduce the environmental impact of electrical installations. In conclusion, understanding and applying the principles of conduit fill is essential for all electrical professionals. It requires a comprehensive knowledge of electrical codes, material properties, installation techniques, and long-term performance considerations. By adhering to recommended fill limits, selecting appropriate conduit and conductor types, and implementing best practices for wire pulling and system maintenance, electrical professionals can ensure the safety, reliability, efficiency, and sustainability of electrical installations. The principles of conduit fill are not static, they evolve with advancements in materials, technologies, and codes. Electrical professionals must stay abreast of these changes through continuing education, professional development, and participation in industry organizations. By embracing a culture of continuous learning and improvement, they can ensure that their skills and knowledge remain relevant and that they are able to deliver the highest quality electrical services to their clients. The principles of conduit fill also have significant implications for the design and construction of buildings and infrastructure. Architects, engineers, and contractors must collaborate to ensure that electrical systems are properly integrated into the overall building design and that adequate space is provided for conduit runs and electrical equipment. This requires careful planning and coordination throughout the design and construction process. The importance of conduit fill extends beyond the immediate confines of electrical installations. It is an integral part of the larger ecosystem of building design, construction, and operation. By embracing a holistic approach that considers the interdependencies between electrical systems and other building systems, we can create more sustainable, resilient, and efficient buildings and infrastructure. The principles of conduit fill serve as a reminder that even seemingly small details can have a significant impact on the overall performance and safety of complex systems. It is through attention to detail, a commitment to quality, and a culture of continuous learning that we can build a better future for ourselves and generations to come.